Hello, my name is Camille Quick, and this is my Physics Lab 4 video, where I will be exploring time-dependent voltage and current in a direct current circuit. The main goals of this lab are to be able to predict the behavior of circuits and then examine the behavior of ohmic resistors and capacitors. The two most important concepts in this lab are the node rule and the loop rule. The node rule exemplifies current conservation and states the total current flowing in a circuit must equal the total current flowing out that same circuit. The loop rule shows energy conservation by stating that in any loop consisting of various circuit elements in a closed circuit, the sum of the voltage differences across the circuit elements must equal 0. This is why the voltage difference of one round trip in a loop equals 0. Another relevant concept is Ohm's law, which states that the current in a circuit between 2 points is directly proportional to the voltage across those same 2 points. In the first part of the lab, I set up a simple series circuit of two 1.5 volt batteries, a 47 ohm resistor, a 100 ohm resistor, and two ammeters. I predicted the currents I1 and I2 to be 0.2 amps by using the node and loop rules. Since the current flowing in must equal the current flowing out, I1 must equal I2. I used a clockwise loop starting from the top battery and also the fact that the two resistors were in a series to conclude that the current was 0.2 amps in I1 and I2. My predictions were correct since both ammeters measured 0.2 amps. It is also important to observe that even when the ammeter is inserted backwards or reversed, the reading is still the same. I replaced the top ammeter with a voltmeter, which measures the voltage between 2 points, and it read 3 volts while the ammeter read 0 amps. These values make sense because for the voltmeter, the batteries are the only source of voltage and that the current is flowing from negative to positive, and for the ammeter, the circuit is open. After closing the circuit, I used the voltmeter to measure the potential differences across the circuit, and those values are listed on the right. As a sanity check, the sum of all those potential differences should equal 0, in which it does. This is an approximate graph of potential versus position around the circuit that again shows the total potential difference in the circuit is 0. An important note is that attaching the voltmeter does not change the current because it has no resistance. But if I were to replace the voltmeter with an ammeter in parallel with the 100 ohm resistor, we would see the current increase in that ammeter because the electrons in the current prefer the path with the least resistance. Using my potential difference measurements and Ohm's law, I calculated the resistance of the following circuit elements. In this portion of the lab, I observed how capacitors charge and discharge. I set up a simple circuit of a 10 ohm bulb, a 9 volt battery, and a 200 millifarad capacitor. After I connected everything, the bulb lights up but dims very quickly, and the current flows counterclockwise. When I disconnect the battery and then close the circuit, the light bulb takes a bit longer to dim. Also, the capacitor discharges and the current flows in the opposite direction. I timed how long it took for the capacitor to charge and discharge using a 10 ohm bulb as well as a 20 ohm bulb. Overall, it took longer for both processes with the 20 ohm bulb. In this portion of the lab, I analyzed the process of a capacitor discharging in terms of potential and ultimately find the time constant of the circuit, RC, at which the voltage difference has dropped to 1 over E of its original value. I set up a circuit with a 9 volt battery, a 2 millifarad charged capacitor, and a 30 ohm bulb and collected time measurements while the capacitor was discharged. I plotted 20 seconds worth of voltage versus time data on a ln of delta V over delta V naught versus time plot, where delta V naught is the initial voltage difference across the capacitor at time t equals 0, which is 9 volts. I calculated my delta V by taking the natural log of the voltage at time t and divided it by delta V naught. After plotted the points, I calculated RC from the slope and got 0.5999 as my time constant, which is almost exactly the theoretical value, which is 6. If I were to use an actual ammeter, which has a small amount of resistance instead of an ideal simulated one, the measured currents would have a smaller value since less electrons would flow through that path. If I used a real battery to charge a real capacitor with no resistor in the circuit, then the capacitor would fully charge very quickly. However, this would not happen in real life because the battery and the capacitor would have some resistance.